Hi and Assalamualaikum all. For this video, I'm going to talk about Laplace transform. And now we already go for chapter 4, part 1. Okay, so this is basically what I'm going to talk in my slides today. First, the introduction. I'm going to recall some of your knowledge on time domain function as well as frequency domain function. And then I'm going to talk about the definition of Laplace transform as well as inverse Laplace transform. Then I'm going to explain on the properties of Laplace transform, which are basically quite similar with Fourier transform. So basically, Laplace transform is about a transformation from the time domain in which inputs and outputs are functions of time to the frequency domain, where the same inputs and outputs are functions of complex angular frequency in radian over unit time. So basically, the keyword here is the transformation from time domain to the frequency domain in the functions of complex angular frequency. Basically, Laplace transform provides an alternative functional description that often simplifies the process of analyzing the behavior of the system. So similar to the Fourier transform, Laplace transform also provides a simplification of analysis process in terms of the frequency domain if compared to analysis in time domain, which is always more complex. And in terms of the application, there are several distinctions that we can see from the application of Laplace transform and also Fourier transform. In engineering, Laplace transform is used to solve complex differential equations. Okay, so this is the keyword, solve complex differential equations that used to model an engineering system. Laplace transform is also used to generate the transfer function representation of a system such as electrical circuit and control system. So this is another keyword. So basically there are two important applications of Laplace transform as compared to Fourier transform: solve complex differential equations and also generate the transfer function representation of a system. So you need to be able to generate this transfer function, which is the representation of the input and output of a system in terms of Laplace transform. Okay, so basically the transfer function representation gives an algebra relationship between the Laplace transform of the input and output of the system. So we're going to use this transfer function to analyze the electrical circuit and control system, as well as to plot the Bode plot in the later chapter. Okay, so here in the table here list all of the some of the differences between a Fourier transform and also Laplace transform. Okay, let's see for Fourier transform first. For Fourier transform, both signal in time domain and its spectrum in frequency domain are one-dimensional complex function. However, for Laplace transform, complex function is defined over a two-dimensional complex plane called S-plane. So this differentiate between Laplace and Fourier, and this S-plane is spanned by two variables, real and imaginary axes. Fourier transform convert time domain signal into frequency domain in the function of angular frequency. However, Laplace transform convert time domain signal into frequency domain in the function of complex angular frequency. And the main purpose of Fourier transform is used for converting non-periodic signal into its frequency spectrum for manipulating them in frequency domain. Or in other words, we want to analyze the signal, so the analysis is easier to be done in the frequency domain as compared to the time domain. However, Laplace transform is mainly used for solving problem involving differential equation and integral equation. Okay, later on we will see, for example, a higher order level of differential equation. If you want to solve it in time domain, it will be much more complex as compared if we solve the differential equation, especially the higher order level. If you solve it in a Laplace transform, it is much easier. Okay, so basically the solution or the process step by step process to solve the differential equation using Laplace transform, there are three steps altogether. First, Laplace transform operation will transform the differential equation in t domain to the s domain function. So t domain here is the time domain. So we transform the time domain function of this differential equation to the Laplace domain, which is in S domain. So this is something that you have to remember. For Laplace transform, we are talking about S domain. And the equation in S domain will be solved using conventional algebra solution. Means that plus, minus, the division and multiplication is a conventional solution. Okay, but we will solve it in S domain. And then we use the inverse Laplace transform to change the solution in the S domain to the T domain function to produce the desired differential equation. So now we already solved the by the step 3, we already solved the differential equation in T domain. So by using this method, Laplace transform made the solution for the differential equation much easier. Okay, so to recall your knowledge, when we're talking about time domain function, it's basically all the expressions or equations that are related to time, which is t. So if you see x t here, for example, of the time domain function, if there is a t element here, you know that this t relates to time, so in function. So a change in time will cause a change in certain variable that is time domain function. Okay, the equation on the right hand also should contain t. Okay, because any changes in t here will also cause a change in the certain variable for this x and also y. Okay, so for the differential equation in time domain forms, okay, these are some example of differential equation for the first order and also second order of differential equation. So basically, if you recall your knowledge to solve this differential equation in time domain, it will be quite complex, right? So this will be more difficult if, for example, if you see question B here, if RT here, okay, is not equal to 0. If it is equal to 0, we call it homogeneous equation. If it is not 0, if it is non-zero value, it is non-homogeneous equation. So it will be more difficult to solve the non-homogeneous equation for the differential equation. So that is why we use Laplace transform, which is much simpler to solve this kind of equations, differential equations. Okay, so in Laplace transform, frequency domain is called S domain. Okay, if we see the diagram here, we have time domain function yt. So when we transform it using Laplace, it will become capital Y and also S because it is in S domain. So all the manipulation of mathematical equation is done in this domain, and then we need to perform the inverse Laplace transform to obtain back the original equation, which is yt. So the real answer in t domain is obtained from the inverse Laplace transform. Okay, this flowchart basically shows the process of differential integral equation solution in S domain and also T domain. Okay, similarly like what I have explained before, first when you have differential or integral equation, perform the Laplace transform. Okay, so it become a transform function. So there will be initial condition, which we will also learn in the later chapter. Okay, there will be an initial condition to be put in this transform function, and all this algebra manipulation is being are being done in this frequency domain or S domain. Okay, so it will, after the manipulation, it will become a modified transform function. Then we need to perform the inverse Laplace transform back to the time domain, which is the solution. So although you'll see that the process is much more than the classical solution, however, it will be much more easier when we compare to solving this differential integral equation in the classical solution, which is the time domain. Okay, so let us see the definition of Laplace transform. Let's say we have ft, which is a function in time domain t, and for our Laplace transform for this chapter, we will only consider when t is equal or bigger than 0. Okay, so please take note of this thing. We will only learn about unilateral Laplace transform, which means that we only consider the positive side of time domain. So its S-domain function fs is obtained by fs equal to Laplace of ft, which is equal to the integration from 0 to infinity, the time domain function, which is ft, multiplied by exponent negative st dt. So L here is the Laplace operator. If in the Fourier transform we have f, in the Laplace transform we have L. So please do not make mistake between Fourier transform and also Laplace transform. Okay, don't confuse between those two. Okay, we look at the example here. Given ft is equal to 1 where t is bigger than 0, it means that we only consider the unilateral Laplace transform when t equal or bigger than 0, which is the positive side of the time domain. Okay, so find the function ft in S domain. So if we perform the Laplace transform using this integral, okay, we need to integrate from 0 to infinity the function ft, which is 1 multiplied by exponent negative st. So basically we take out the exponent negative st and it becomes negative 1 over s here, and put the value of 0 to infinity, we will get 1 over s. So the Laplace transform for 1, which is a unit step function because it is considered only when t bigger or equal to 0, is equal to 1 over s. Okay, another example, you need to find the Laplace transform for ft equal to 3 exponent 70 where t bigger than 0. So in other words, this function 3 exponent 70 is being multiplied with unit step function. Okay, so if we put in the equation for ft, basically this ft is equal to 3 exponent 70 multiplied by ut, because it is only on the positive side of the time domain. So for the solution, we integrate between 0 and infinity ft multiplied by exponent negative st dt. Okay, put in the value for ft, okay, and integrate it. Okay, integrate this equation. Okay, so this is only in time domain. So when you integrate, put in the value of 0 and infinity, you will get 3 over s minus 7. Okay, this is when you want to perform Laplace transform using the integration. Okay, however, okay, for this chapter, similar to Fourier transform, we will not going to test you to perform the Laplace transform using the integration in time domain. This is because you will be provided with the Laplace transform function table. What you have to do is just to find the solution in the table that reflects the time domain function that you want to transform. For example, unit impulse function, which is delta t, the Laplace transform here, if you perform the Laplace transform here, you will get 1. Okay, for unit step, okay, unit step function, if you remember unit step, okay, this is unit step, which has value of 1 when t bigger than 0. Okay, the Laplace transform is 1 over s. Okay, so you can have a look on the table of the list of Laplace transform and also their pairs. Okay, and also the Laplace transform properties. Okay, it's in the table D and also D2. Okay, and we have many more functions there. So these are some of the examples of the function and also the transform, the Laplace transform in S domain. Okay, so again, basically, you do not have to perform the integration of Laplace transform just like this. Okay, this is to show you how we obtain from time domain and we transform it using integration. Okay, to transform it into Laplace transform, then we will get 3 over s minus 7. So if you compare this, okay, with the table, you will see that this one is 3 exponent 70. Okay, sorry, this is not. Okay, this is in the table. So we can use these properties. Okay, exponent negative 80 ut. So basically, in this example here, a is negative 7. Okay, a is negative 7. Why negative? Because in the original here, a is like this. Okay, it's positive. So if a is negative 7, this one will become 1 over s minus a. So this is 3 over s minus 7. Okay, we'll look at another example. Find the Laplace transform for the functions below using the table given. So given that ft equal to tut, okay, so the Laplace transform fs will be equal to 1 over s squared. So how did I obtain this value? Okay, so you have to refer back to the table. Okay, Laplace transform function table. So for tut, the s domain here is 1 over s squared. Okay, so as simple as that, you can put the equation, the solution, which is 1 over s squared. So this one is exponent ATUT. So this one, the answer will be Fs equal to 1 over s minus a, right? Right. In order to transform back the Laplace transform, we need to perform the inverse Laplace transform. Okay, so to transform Fs into Ft, which is time domain. So this is how we write the equation. Ft equals to inverse Laplace transform of Fs. So L minus 1 here shows the inversion process. So you need to put this symbol to show that you are doing inverse Laplace transform. So when we want to do in terms of integration, we need to multiply by the integration here with 1 over 2 pi j. And then integrate between negative j infinity to j infinity Fs exponent stds. I think there is a slight mistake in your notes here. There is a t here. There shouldn't be t here. Okay, it should be Fs exponent stds. So this is if we want to perform in terms of integration. Okay, however, we can, like I said before, we can use the what we can use is the table, the list of the table, and we mesh from the Laplace transform pairs. Okay, just like when we did it before in Fourier transform. So for example here, determine ft if fs is given as 3 over s squared. Okay, so we put in terms of inverse Laplace transform symbol here, negative 1 fs. Okay, so put the value fs, which is 3 over s squared. Okay, 3 is a constant, so you can put it out, okay, outside the inverse Laplace transform symbol here, and we leave only 1 over s squared. So we know that from the table, okay, this refers to tut. Okay, so if you refer to the table, you can see that on the left side there is a signal in time domain, and on the right side there is a Laplace transform in S domain. So in order to find the Laplace transform, you match the signal here, find the signal which looks similar to the signal that you want to obtain the inverse Laplace transform. Okay, so find on the right side. Okay, and then you will be able to obtain the inverse Laplace transform, which is 3tut, right? From the table. Okay, from the table, the symbol, the signal in time domain is t power of n ut. Okay, and the Laplace domain is n, okay, a factorial, and divided by s n plus 1. Okay, so from here you can match that with the signal here. So n plus 1 is equal to 2, so n should be equal to 1. So this is where you can get TUT, okay, for the answer. Okay, now, so to twist this question a little bit, given Fs equal to 1 over s plus 1 and Gs is equal to s, you need to find Gt. Okay, which means that you need to perform inverse Laplace transform. So Gs is given as Fs, so put the value of Fs, it will become s, okay, because we multiply by s here, divide by s plus 1. Okay, so you need to be able to put in the form that you can perform the inverse Laplace transform, because if you see from the list of tables, you cannot find the time domain, okay, that can match this form of Laplace transform, which is s divided by s plus 1. Okay, so what you have to do is you rearrange this equation so that it will become the equation that you can perform the inverse Laplace transform. Okay, so how do you get this? Okay, there are many ways to to get this equation. Okay, so one way here is you put the value, okay, you rearrange the equation so that this will become 1 over s plus 1. Okay, one part of this equation will become 1 over s plus 1, because from here you can use the inverse Laplace transform. Okay, inverse Laplace transform for the equation. If you look at the table, there is a function exponent negative at ut, in which you can have the Laplace transform of 1 over s plus a. Okay, so the numerator here should be 1. Okay, should be 1 and not s. Okay, so here, okay, what you can do is you arrange, for example, here, what I will do is, okay, I will put something like this, minus 1 divided by s plus 1, which is basically 1 minus 1, okay, plus s divided by s plus. Okay, so this one will become 1. Okay, so you open up this bracket. Okay, we will get 1 minus 1 minus correct this one, s minus 1 plus s divided by s plus 1. Okay, as we combine these two, okay, so we get minus s minus 1 plus s plus 1. Okay, so basically you will get 1 minus 1 divided by s plus 1. So from here we can match from the inverse Laplace transform pairs 1. Okay, if the Laplace transform is 1, the pair should be delta t. Okay, delta t, if we perform the Laplace transform, it will become 1. Okay, so for the inverse Laplace transform, you will look at the right hand side and then match it back to the left hand side. So gt will become delta t minus exponent negative t ut. Okay, so a here should be 1. Okay, a here should be 1, so exponent negative t ut. So don't forget this ut, because it shows you the unilateral Laplace transform. Let us see more examples. Okay, for this exercise, okay, find the inverse Laplace transform first for Fs equal to 1 divided by s squared plus 25, and question number 2, Fs equal to 2s divided by s squared plus 10. So to solve this, you need to find the Laplace transform pairs that can match this Fs. Okay, for the first question, 1 divided by s squared plus 25. So what I found out is from the table. Okay, from the table, I find that assign omega t ut, when you perform Laplace transform, okay, you will get omega divided by s squared plus omega squared. So basically you can match with this Fs, okay, and also notice there is no s at the numerator here. So Fs here is basically 1 divided by s squared plus 5 squared. Okay, plus 5 squared. So how do we want to put 5 at the numerator here so that it will match this omega? Okay, so that it will match this from the table, sine omega t ut, and the Laplace transform will be omega divided by s squared plus omega squared. Okay, so basically we can multiply by 5 over 5. Okay, so that this 5 we can put it here. So this one will become 1 divided by 5. 5 divided by s squared plus 5 squared. Okay, so from here you can perform the inverse Laplace transform of fs. Okay, so basically this is 1 over 5, which is the constant, and inverse Laplace transform of 5 divided by s squared plus 5 squared. Okay, so this one is 1 over 5, and the omega here should be 5 sine 5t, and don't forget this ut. Okay, so this is for question number 1. For question number 2, this is fs equal to 2s divided by s squared plus 10. So you notice there is s here. Okay, so if you find from the table, you look at the table and you find that from the table, okay, from the table, cos omega t ut, and the Laplace transform will give you s at the numerator here, divided by s squared plus omega squared. Okay, so to perform the inverse Laplace transform of fs, okay, it should be 2 here you can put as the constant. Okay, so inverse Laplace transform of s divided by s squared, and to make this s omega squared, what you can do is you put squared 10 squared, right? Square root 10, and then you square again, you will get 10. Okay, so this should be 2 cos square root 10 t ut. Okay, so this is the answer for question number 2. Okay, next we are going to learn one by one the properties of Laplace transform. So from linear operation to the modulation, and there will be one more here, the time transformation and also time scaling. Okay, first for the linear operation, okay, this is similar as the Fourier transform as well. So if there are two time domain function, for example f1t and f2t, and a and b here are constant. Okay, so the Laplace transform of a f1t plus b f2t is equal to a, which is a constant, multiplied by f1s plus b, which is a constant, multiplied by f2s. Okay, so this is the proof of how you obtain from this Laplace transform of time domain, okay, to the Laplace domain. Okay, this is the proof, so I'm not going to go through it one by one, but basically it shows you here the integration is being done for one part first, which is the f1, and then another integration for this should be f2. Okay, this should be f2, and then you will obtain a f1s plus b f2s. Okay, so this is the linear operation. And for the example here, given f1t is equal to hyperbolic cos at equal to exponent at ut plus exponent negative at ut divided by 2. Find the Laplace transform for ft. So in order to find the Laplace transform, you separate this into two equations. Okay, first is 1 over 2 exponent at ut, another one is 1 over 2 exponent negative at ut, and 1 over 2 here is the constant, okay, which refers to a and also b in the previous slide. Okay, and then find the Laplace transform of exponent at ut. Okay, this is a constant. Find the Laplace transform of exponent negative at ut. Okay, you will get this, and rearrange back the equation, you will get s divided by s squared plus a squared. Okay, there's another example here. Given that fs equal to 3 divided by s squared minus 4s plus 3. Okay, find the inverse Laplace transform for fs. So first of all, in order to perform inverse Laplace transform, we need to factor this equation. Okay, we need to factorize this. So it will become 3s minus 3 s minus 1. So I hope you know how to get from here to here. Okay, I'm not going to show you. Okay, this is something that you should know, that you've learned from engineering mathematics. So this one, we can put it as a divided by s minus 3 plus b divided by s minus 1. So you need to use the knowledge that you learn from engineering mathematics to perform the partial fraction theorem, okay, in order to obtain A and also B. Okay, so this is how I perform the partial fraction theorem. For example, Fs here is given as A divided by S minus 3 plus B divided by S minus 1. Okay, so in order to get A, I will multiply Fs by S minus 3. Okay, and S here should change to 3. Okay, because we want to cancel out this denominator here. So s minus 3 should be equal to 0. So s will become 3. Here you put the whole equation, which is this. Okay, 3 divided by s minus 3, s minus 1, s minus 3, and s equal to 3. Okay, so put the value 3 here. You will get 3 divided by 2. Okay, so similarly for B, okay, you multiply 3 divided by s minus 3, s minus 1, multiplied by s minus 1, which is the denominator at B here. S should be 1. Okay, so this one, put the value of s. This one will become negative 3 over 2. Okay, so from here you put the value in Fs. Okay, so it should be Fs equal to A divided by S minus 3. So 3 over 2 multiplied by 1 S minus 3 here. And there's another one here. So 3 over 2 here is the constant. Okay, so you should perform the Laplace transform for 1 divided by S minus 3. Okay, so from the table you find out that you can use the pair of exponent negative at ut, and when you perform the Laplace transform is 1 divided by s plus a. So use this, find a here. So a here should be, for the first one should be a negative 3, the second one should be negative 1. So you put in the value, so exponent 3t, and this one is exponent t. Okay, multiply by ut. So this is the answer for exercise 2. Now we go to the application, the important application of Laplace transform, which is the differentiation. Okay, so if ft for t bigger than 0 has differential form of dft dt, then the Laplace transform will be Laplace of the differentiation of f over dt is equal to fs minus f0. Okay, f0. So f0 here is the value of ft at time equal to 0 or initial condition value. So this is what we call initial condition value. Okay, so we will learn how to obtain initial condition value in the next part of Laplace transform. So for the proof, this is the proof how you obtain the Laplace transform of differential equation using the integration. Okay, using the integration, you integrate of dft dt and multiply by exponent negative st dt. Okay, so when you integrate this, you will obtain like this. Okay, and this is sfs. Put in the value and you will get sfs minus f0. Okay, and if you try to do it for higher order differential form, okay, you will get, for example, for second order differential form, okay, you will get the Laplace transform for second order differentiation is equal to s squared fs minus sf0 minus df0 over dt. And for third order, you will get longer equation, and generally for nth derivative of ft, it will become, okay, for n order differential form should be this equation. Okay, so you just put in the value. So again, you don't have to perform the integration to obtain the Laplace transform of this differential equation in time domain, but you have to refer to the list of table at the differentiation properties. Okay, and then you need to be able to use the equation, okay, the formula given. For example, here, if you want to find the second order differential form, so you will replace n here with 2. Okay, so you just put in the value here. Eventually, the equation should not be too long for 2. It should be something like this. Should be like this. Okay, because when you put in the value, some of the values here will be cancelled because of a 0. Okay, so you will get like this. Right? Okay, let's see some example here. This is the value that I took from the table. Okay, so from the table, you will see the formula like this for the differentiation properties. So for this example, given that x double prime t, which is the second order of differentiation, plus 3x prime t plus 2xt equal to 0. So I hope you understand this one should be second order of differentiation. So this one should be the square xt over dt squared. Okay, which is the second order, and this is the first order. So this one should be dxt over dt. Okay, some of the mathematical symbols use the double prime or prime here. Okay, find xt given the initial condition. This is the initial condition here. Okay, this is also the initial condition when when t is equal to 0. Okay, so when t is equal to 0, at 0 is given as 1, and so when t is equal to 0, d at c dt is given as negative 4. So you put in the value. Okay, so in order to get this, you use this formula. Okay, replace n with 2. So you and fs here replace to xs according to the equation. If the equation put ft, then you put fs. If the equation give you at, then you put as. So now xt, you put xs. So for this, only for this, x double prime, this is the equation. Okay, x squared xs minus s at 0 minus x prime 0. So for 3x prime t, this is the equation. Okay, for this, and then 2xt is 2xs. Basically, you Laplace the whole equation, this whole equation, you perform the Laplace. Okay, perform the Laplace transform. So when you Laplace 0, it's also 0. Unless 0 here has another values, if it is non-homogeneous equation, there will be value here. But if it is homogeneous equation, it will become 0. So you put in the values of initial condition. We'll get the initial condition from here. Okay, so you can put the value of x 0 and x prime 0. You put the value and you rearrange so that xs is outside the bracket. You will get inside the bracket s squared plus 3s plus 2. And this one doesn't have any xs, doesn't multiply with xs. Okay, so you rearrange so that xs on the left and all other values are on the right. Okay, so you will get something like this. And how to get here? From here to here, of course, you perform partial fraction theorem. So it is important for you to show step by step. Okay, I do not want to accept answer where you just put the final value of Laplace transform. I need students to show step by step on how you obtain this value. Okay, and then once you obtain this, then your work will become easier because you can just inverse the Laplace transform of xs, so that you will get 3 exponent negative 2t ut minus 2 exponent negative t ut. So again, for this one, you refer to the pairs of exponent negative at negative AT UT, and the Laplace transform here is 1 over S plus A. Okay, so this is the final value. And remember, when the question give you the differential equation, the final value you should find is in time domain. So you have to find xt, not xs. Okay, you cannot leave your solution up until xs. You need to perform the inverse Laplace transform to get xt. Okay. Exercise 3, I need you to try this by yourself, and you can compare later your answer with my answer. So I'm not going to show you here. And the next property is integration. Okay, the integration properties can be used if Fs is the Laplace transform of Ft. Okay, for example, if you want to perform the Laplace transform for the integration of this, okay, you just need to find the Laplace transform for Ft first, which is Fs, and you divide by S. Okay, again, so this is the proof using the integration on how you obtain the Laplace transform for the integration of Ft. So there are double integration here. Okay, two level of integration. First, you integrate the Ft, and then you integrate the Laplace transform. Okay, meaning that you perform the integration for the Laplace transform. Okay, so you will get Fs over S. So if you see the equation here, basically what you have to do is find the Laplace transform of the original function, which is Ft, but it is not over yet because you need to find the Laplace transform for the integration of Ft. Okay, so in order to get that, you just have to find the Laplace transform for Ft, which is Fs, and you divide by S. So as simple as that, right? And then for the time shifting, okay, if Laplace transform has the form of Fs, okay, if the Laplace transform of Ft has a form of Fs, then if there is a time shifting in the time domain for F, which is shifted by T naught, then you have to multiply the Laplace transform of Fs with the exponent negative T naught S. Okay, reply the value of T naught here. Okay, let's see the example here. Find the Laplace transform for this impulse Ft equal to 1 from T for T from 0 to C. So basically this is the impulse function. If you want to draw this, you see here, for T between 0 and C, see the value here is 1. So basically this is the square function. Okay? Sorry, not impulse function, but impulse means here is a square function. Okay, T. And Ft equal to 0 for another T. Okay, so apart from 0 to C, the value is 0. So basically, when you want to perform this, unlike Fourier transform, which give you shape of the signal and also the pairs of Fourier transform, Laplace transform table does not give you that. So means that you have to find the equation of this shape of the signal in the equation that you can solve the Laplace transform. Okay, so this square can also be represented by unit step function. Okay, so if you if you derive the equation for this square function, you will get ut minus c. Okay, so this, when you see the unit step function in the form of this, you should know that it is actually square function. This is actually, okay, so I recall back your memory in the chapter 1. So let's say if you have ut minus ut minus 5. Basically, this is the rectangle function, the square function of rectangle if the value is, if the shape is more to rectangle. So this is from 0 to 5. So if ut minus something, for example, you should be able to draw the rectangle function based on the time here. Okay, so pandai-pandai lah. Okay. to draw the rectangle function here. Okay, so when you obtain the equation like this, we know that we can solve this using the unit step function and also time shifting properties. Okay, so you separate these two equations to become a ut, and another one is ut minus c. So you perform individually the Laplace transform. This one should be 1 over s. This one, because there is a time shifting here, and we know that Laplace transform for ut, okay, which is the original ft here, is 1 over s. So this one should be 1 over s, and because of the time shifting, you multiply it by exponent negative t naught s. So t naught here refer to c, so exponent negative cs. Okay, so this is the answer for Laplace transform of this ft. Given fs equal to 2 over s squared minus 2 exponent negative 2s over s squared. Find the inverse Laplace transform for fs. So this is where you have to be creative. For Laplace transform, in order to find the inverse Laplace transform, you need to be creative. Okay, when you cannot find the exponent function here in the s domain, if you refer to the list of formulas, you cannot find in s domain. So we know that this one is actually time shifting. Okay, it has go through the time domain function has go through the time shifting. That is why in the Laplace transform it has this exponent function. So from the table, if ft is equal to t, then fs equal to 1 over s squared. So we can regard ft equal to t as the original function of fs, okay, as the root function of ss, and ft minus t naught ut minus t naught, the Laplace transform is fs exponent negative s. Okay, so you mesh with this exponent negative s t naught. T naught here is 2, so you perform the inverse Laplace transform for this individual equation. Here you will get 2 tut, and here you will get 2 tut as well. However, it has been time shifted by 2. So you have to put negative 2 t minus 2 ut minus 2. Okay, so this is how you want to find the inverse Laplace transform for the time shifting properties. Okay, the keyword is you have to be creative. Okay, there's another example here. Consider the exponential function which has the equation of ft equal to 5 exponent negative 0.3 t, and this function is delayed by 2 seconds and multiplied by ut minus 2 to become f1 equal to 5 exponent negative 0.0 t minus 2 ut minus 2. Okay, so basically when you see this, you see the equation and also the question. This function is delayed by 2 seconds. Okay, so at every t you should minus 2, okay, multiplied by ut minus 2. So to become like this. Find the Laplace transform for f1t. Okay, and there's another question. Okay, exponential function as well, but this one is just multiplied by ut minus 2, and the t here at the exponential function does not have minus 2. Okay, so we look at the solution here. Okay, so for the first solution, we know that this when we see the exponent function, we can use the ft equal to exponent negative 8 to find the Laplace transform partners. And also when we see the shifting in time domain, we can use the time shifting properties. Okay, so straight away, solution for question number 1, we just mesh with this equation. So a is equal to here 0.3 and t naught is equal to 2. So you will get first f1s, which is the exponent function, only exponent function without the time shifting. So it should be exponent negative 2s, exponent negative 2s. For the exponent function here, it should be this one. Okay, the Laplace transform should be 1 divided by s plus 0.3, because there is 5 here. So 5 divided by s plus 0.3. So that is fs. And for the time shifting, then only we multiply by exponent negative st naught. So this is exponent negative to s. Okay, so this is the solution for the question 1. For question 2, it is a bit tricky because this t here does not have t minus 2. So you cannot use straight away the equation from here. Okay, so what you can do here is you rearrange. This is how you rearrange to make t here become t minus 2. Okay, so basically this 5 exponent negative 0.3 t ut minus 2 you multiply by, what is this? Okay, if you put this exponent function, if you solve this one should be 1. 0.6 multiplied by exponent negative 0.6, exponent minus 0 should be 1. So this, like I said, you have to be creative. So when you multiply like this, okay, so you rearrange so that you can put exponent negative 0.3 t minus 2 ut minus 2, and this one become constant. This one should become constant. Okay, so this one will become 2.744. You just solve this without performing any Laplace transform, because this is just constant, and then this one have the same form. Okay, so again, for this part is similar to this part, okay, without the constant. Okay, and then multiply back by the constant 2.744. So this is the value for the Laplace transform of f to s. Okay, this should be f to s. Right. Okay, now we are going to do, we're going to look at the frequency shifting properties. If ft has a Laplace transform of fs, then if there is any exponent function multiplied by ft, this one should reflect the frequency shifting at the time domain. Okay, so the Laplace transform should become fs minus a. So don't be confused with the time shifting, because the Laplace transform pairs is actually opposite from the frequency shifting. Okay, if you match or if you observe the time shifting properties and also the frequency shifting properties, the Laplace transform for both of these is actually opposite from each other. Okay, so as an exercise here, find yt if ys is equal to s squared minus 6s plus 8. In order to solve this, actually this is this is similar examples as before. In order to solve this, you need to perform the factorize. So this one should be equal to a divided by s minus 4 plus b divided by s minus 2. Okay, this one should be s minus 4, s minus 2. Okay, so you should know how to factorize from here to here. Right, so you perform the partial fraction theorem. From the partial fraction theorem, you will get a equal to 2 over 3. Okay, so this one should be 4. And b should equal to 1 over 3. 1 over 3. 1 over. Okay, so this one, for this frequency shifting, you can also what you call it, refer, if you mesh with the Laplace transform pairs for exponent function, it should be quite similar, right? And then from here, you perform the inverse Laplace transform for ys. You get 2 over 3 exponent negative 4t ut plus 1 over 3 exponent negative 2t ut. Okay, so please try it. Okay, I'm not going to show you one by one here. Okay, should be able to perform this by now, right? Okay, there's another example here. Find the Laplace transform of the signal ft given that the signal ft is equal to a exponent negative at cos omega naught t plus theta. Okay, in order to solve this, we need to use the linearity, frequency shifting, together with the trigonometry identities. Okay, so for the frequency shifting, we know that exponent negative at if you the Laplace transform of in form of the fs plus a. Okay, so now we perform the Laplace transform of ft. So you equation fs equal to Laplace transform of a exponent negative at cos this one, you use the trigonometry identities. So when omega naught t plus theta, it will become cos omega naught t cos t minus sine omega naught t sine. So from test 1, you should also notice that you should or you need to be able to apply the trigonometry identities. So please do not forget that formula. Okay, it is given in the list of formula, but please do not forget on how to use that formula, right? Okay, so this one you can separate these two equations here and here, so it will become Laplace transform of a exponent negative at, which we know here is from the what we call it, from frequency shifting. It's 1 cos omega naught t theta. Okay, and then you minus another Laplace transform of a exponent negative t sine omega naught t sine theta. Okay, so from here, when you perform the Laplace transform, then you can use this, and also you can use the cosine. Okay, if you notice at the cosine, okay, for cosine, omega t ut, it will give you Laplace transform of s divided by s squared plus omega squared. And for the sine omega t ut, it will give you the Laplace transform of omega divided by s squared plus omega squared. Okay, basically, even though if you see at the equation here, there is no ut, but like I said before, for our syllabus, we only learn the unilateral Laplace transform. So you should know that this one is actually multiplied by ut, which is the positive side function only. So when you refer also at the table, you will notice all of the equations have ut, okay, which is a unit step function, which reflect only the positive side of the time domain signal. Okay, so from here you can use this. And how about the cos theta here? Okay, the cos theta here is actually constant because it does not involve any t. Okay, cos theta here. So you can actually take it out. So from here we can get a cos theta, which is the constant. Okay, and then because of this exponent negative at, we know that at every s here we should add a. So here it will become, because this is cos omega t ut, right, from this, so it should become here, if we refer to this one as well, s divided by s squared plus omega squared, so should become s plus a divided by s plus a squared plus omega squared. So this is only for the first side, the first part of the equation. So I repeat, a and cos theta here can become constant because it does not involve any t. So you take this out, a cos theta, and then exponent negative at cos omega naught t, you can refer to this and also this. So cos omega t ut should be s divided by s squared plus omega squared. So you can put S divided by S squared plus omega squared. However, because of this, the existence of this exponent negative AT function means that at every S you should add A. So just now we obtained this, right? We use this. So at every S you put you plus with A. So S plus A divided by S plus A squared plus omega squared. So similarly for this side, you take out the A sine theta, and for sine omega t, the numerator here should be omega. So for omega here, it will omega here is actually omega naught if we refer to this. So this is omega naught. At the denominator here, S squared plus omega squared. So this one plus omega squared, but S here you should add by A because of the existence of this frequency shifting property. So S plus A, so this one should be S plus A, then only U squared. Okay, you plus with A first, then only U squared. So sorry, this one should be omega naught. Okay, so this is basically your answer. Okay, your answer for this question, right? So it's much easier if they give the value here so that we can transform A cos theta to the numbers, right? However, this is the value, this is the answer for this exercise. Here is convolution. Okay, similar to the Fourier transform, for Laplace transform, for the convolution process, we just have to multiply between two Laplace transform equation. So if Hs equal to Fsgs, then the inverse Fourier transform of Hs is a convolution between Ft and Gt. Again, in time domain, if there are two functions convolved together, but in Laplace transform, it will become multiplication, which is much more easier than convolution. Okay, for the modulation, the multiplication of the function xt with sine omega t or cos omega t. So if there is a function of xt and the Laplace transform is s for all real values of omega, then if xt multiplied by sine omega t, okay, this is different with the Laplace transform pairs of cosine and sine. Okay, because Laplace transform pairs for sine and cosine is actually sine omega t multiplied by ut. Okay, this is for any function of xt. So first you have to find the function of xs first. Okay, then for every s you have to plus j omega. There should be there should be a close bracket here. Okay, plus omega, and another one is s minus j omega. Okay, and for the cosine function, for the this is for the sine, okay, which has j at the numerator. For the cosine function, it's only 1 over 2. So the equation here is similar. For every s, you have to plus j omega and also minus j omega. So in the end of the videos, I'm going to show you more examples of each of the property. And for time scaling and also time transformation, you just have to put in the value. For example, the time domain function is FAT. So you have to find the Laplace transform for Ft, which is Fs. And then for every s, you have to divide by a. And then multiply all of the equation with 1 over a. Okay? And for the time transformation, you also have to perform like this, time scaling. However, because of the shifting here, you have to multiply by exponent negative st naught divided by a. And we're going to do some exercise here for exercise 6. Okay, for exercise 6, fs is given as like this. So first you have to find Laplace transform of gt equal to exponent negative 3t. So we know that we can use frequency shifting properties for this equation. For this question, we can use frequency shifting. Okay, for the second one, if we look at this, we know that it has undergo time shifting properties. So we use the time shifting. Then we need to find ft. Here we use the inverse Laplace transform. Okay, so let us do one by one here. In order to do this, you refer to the properties of the Laplace transform. So from the properties, you can see that for frequency shifting, exponent negative at ft will give you Laplace transform of fs plus a. Okay, fs plus a. So from here, we already know the fs. Okay, we already know the fs. So for gs, actually equal to Laplace transform of exponent negative 3t ft. Okay, so if we put in the equation here, it's actually fs plus 3. Okay, because a here is 3. So we already know the fs, right, from here. So in every s here, we put s plus 3. So s plus divide by s plus 3, then only you square, minus 7 s plus 3 plus 10. Okay, you can leave like this, or if you want, you can also solve it just a little bit here. S plus 3 divided by s plus squared minus 7s minus 11. So this is your answer for question 1. For question 2, find the Laplace transform for ht equal to ft minus 4 ut minus. So hs is actually equal to Laplace transform of ht. Okay, so you use the time shifting properties of Laplace transform. So for time shifting properties, we know that let me find it first. Okay, time shifting for f t minus t naught ut minus t naught, the Laplace transform pairs here is fs exponent st naught. Okay, so match with these properties. Okay, we also already know the fs here, because you do not have to find the fs, so we just put the value here. Okay, fs exponent, what is t naught here? So t naught here is 4, so exponent negative 4s. So what is fs? Fs is this. So this is fs. So equal to s divided by s squared minus 7s plus 10 multiplied by s minus negative 4s. So just like that is the solution for question 2. For question 3, you have to find ft. Okay, so we know that we can use the inverse Laplace transform, and you can factorize this. Okay, the denominator. So if you factorize this, fs should become s divided by s minus 5, s minus 2. Okay, which is a divided by s minus 5 plus b divided by s minus 2. Okay, so using partial fraction theorem, okay, a equal to s divided by s minus 5, s minus 2. So please do the revision on partial fraction theorem. Okay, I also know that some of you can, if you have the calculator, that you can use the calculator, but you have to show how you obtain the value. Okay, s minus 5, s equal to negative 5. Okay, so because we want to cancel out this denominator at a, so s equal to negative 5. Okay, so replace the value of s with negative 5. Here you will get, sorry, s is not negative 5 here, it should be positive 5. Sorry about that. So this one should be 5 over 3. And for b is equal to s divided by s minus 5, s minus 2, multiplied by s minus 2, and s should be 2. So this one, you put in the value 2. This one should be negative 2 over 3. Okay, so from here, you can get fs equal to 5 over 3, 1 over s minus 5. Basically, you want to get the value of constant here. Minus 2 over 3 divided by 1 over s minus 2. And you perform the inverse Laplace transform for fs. Okay, we will get 5 over 3 exponent 5t ut minus 2 over 3 exponent 2t ut. Basically, so this is the solution. If you done lots of exercises and you will become familiar with the Laplace transform pairs, and you do not have to refer to the table every single time. For example, for this equation, for the exponent function in time domain, there will always be the question about this, okay, for this Laplace transform pair. So you should, when you do lots of exercises, basically you will remember the Fourier transform pairs. Okay, there's another one here. Find the inverse Laplace transform for Fs given as this equation. Okay, so even if it looks similar here, but like I said, when you perform inverse Laplace transform, you have to be really creative. Okay, creative means that you have to find the pairs that can mesh with this. Okay, if you try to factorize, you cannot factorize the denominator here. So what you can do, you rearrange so that it will become equation, it will become in the form that you can perform the inverse Laplace transform. Okay, so from here we know that if there is s squared at the denominator, what you can do, you can also use the either cosine or sine function. Okay, the cosine of sine function, if you look at the table. Okay, if you look at the table at number 12 and 13, it's either cosine or sine function which has been frequency shifting, okay, with exponent negative at. Okay, so from here, okay, I rearrange back the equation so that it will become so that down here I put something that I can factorize. So it will become s plus 2 plus 1 divided by s squared plus 4s plus 4 plus 1. Okay, so this one s plus 2 plus 1 down here at the denominator here. Now you can actually factorize this to become s plus 2 squared. Okay, so from here you can separate these two equations. We become s plus 2 divided by s plus 2 squared plus 1 plus 1 divided by s plus 2 squared plus 1. Okay, so basically from here you can mesh with the table. Okay, Laplace transform pairs from the table. You can see at the exponent negative at cos omega t ut, which will give you Laplace transform of s plus a divided by s plus omega squared. Okay, so look similar, right? The form looks similar. So what you have to do is just match. Okay, sine omega t ut, and the Laplace transform is omega divided by s plus a plus omega squared. Okay, so from here, what we can do here is perform the Laplace transform individually for each of these equations. So ft here is inverse Laplace transform of s plus 2 divided by s plus 2 squared plus 1 plus inverse Laplace transform of 1 divided by s plus 2 squared plus 1. Okay, here we mesh with this, you can get exponent negative 2t cos t ut plus exponent negative 2t sine t ut. Okay, so we can factorize this cos t plus sine t exponent negative 2t ut. Like I said, when you want to find the inverse Laplace transform, not all the time you have to perform the partial fraction theorem. Okay, if it's something here that you can, if at the denominator here you cannot factorize, then you can be creative and try to rearrange the equation so that you can factorize the denominator. Okay, and then when you factorize this, then you know that you do not have to perform the partial fraction theorem, but you can refer to the cosine or sine function, okay, at the time domain, and find the Laplace transform pairs. Okay, from here you will get this. Okay, and for exercise 8, I want you to try by yourself, and you can PM me to check your answer with me. Okay, So I think that's all for today. If you have any question, then you can PM me directly. Thank you.